red flags in the data, anomalies that multiply with every observation, behavior that defies explanation. And deep in the cold beyond Mars, an object from another star system is forcing scientists to ask a question they never expected to confront. Could 3I Atlas be something we've never encountered before? This isn't clickbait. This isn't sensationalism. This is the actual question that NASA researchers are now privately discussing as telescopes worldwide track an interstellar visitor displaying characteristics that match no known category of celestial object. The latest updates paint a picture that grows stranger by the day. Sudden brightness flares with no thermal explanation. Negative light polarization never measured in any previous comet. Internal activity at temperatures where all known volatiles should be frozen solid. And now, irregular outbursts suggesting something happening beneath the surface that our models cannot account for. When astrophysicists use the phrase, "we don't yet know why," they're not being cautious, they're being honest. Because the data coming from 3I Atlas doesn't fit any framework we've built to understand comets, asteroids, or any other natural solar system body. Late 2024, the Atlas survey in Hawaii detects a faint object moving through the constellation. Initial orbital calculations reveal a hyperbolic trajectory, the signature of an interstellar visitor, the third ever confirmed in human history, following 1I Oumuamua in 2017 and 2I Borisov in 2019. The astronomical community takes notice but expects familiar patterns. Oumuamua was inert, showing no cometary activity. Borisov behaved like a textbook comet, predictable and conventional. Scientists anticipate that 3I Atlas will fit somewhere within that spectrum. Instead, it fits nowhere. As it approaches the inner solar system throughout 2025, observations begin revealing contradictions. NASA's Neil Gehrels Swift Observatory detects sustained ultraviolet emissions from its coma. Hydroxyl radicals, the chemical fingerprint of water molecules being shattered by solar radiation. But the distance is wrong. 3 astronomical units from the Sunday, a region where temperatures hover around negative 150 degrees Celsius. Water ice should be completely stable. No sublimation, no activity, no hydroxyl signatures. The detection forces a question. What energy source is driving this activity? Subscribe now, because what comes next challenges everything we thought we understood about interstellar objects. Hubble Space Telescope imaging confirms the impossible. A structured jet erupting from 3I Atlas nucleus, not random outgassing. A directed plume oriented roughly 10 degrees toward the solar apex, releasing material at rates measured in tens of kilograms per second. Every existing cometary model says this cannot happen at this distance. The thermal energy from sunlight is insufficient to sublimate water ice. Even carbon dioxide, which transitions from solid to gas at lower temperatures, should remain stable. Yet the measurements are unambiguous. Material is venting into space. The coma is growing. The jet persists across multiple observation sessions spanning weeks. Scientists begin proposing explanations. Perhaps radioactive decay within the nucleus generates internal heat. Perhaps exotic ice compositions sublimate at temperatures lower than standard volatiles. Perhaps subsurface pressure has built up over millions of years and is now venting through surface fractures. Each theory faces immediate problems. Radioactive heating requires specific isotope ratios, unlikely in a body that formed billions of years ago. Exotic ices still require some threshold temperature to transition phases. Pressure venting should be explosive and brief, not sustained and steady. The James Webb Space Telescope adds another layer of mystery. Its infrared spectrometer reveals a carbon dioxide to water ratio of approximately 8:1. In typical solar system comets, water dominates, usually comprising 70% or more of volatile content. This inverted chemistry suggests 3I Atlas formed in an environment fundamentally different from anything in our planetary neighborhood. A colder star, Perhaps a red dwarf with barely 20% of our sun's luminosity, a protoplanetary disk where carbon compounds froze preferentially. Conditions utterly unlike those that shaped objects in our own system's formation. But this raises another question. If carbon dioxide dominates, and carbon dioxide does sublimate at lower temperatures than water, why wasn't this activity predicted? Why did every model fail to account for it? Because at 3 astronomical units, even carbon dioxide should remain frozen. While space-based telescopes tracked the chemistry, ground-based observatories in Chile detected something unprecedented. The European Southern Observatory's Very Large Telescope, using polarimetric instruments, measured how light scatters off the dust particles in 3I Atlas coma. The result, negative polarization. In every previously studied comet, dust grains scatter sunlight in predictable ways. The angle and degree of polarization reveal particle size, shape, and composition. But 3I Atlas dust bends light in the opposite direction from normal, a configuration never recorded in any interstellar object before. This implies the particles are either extraordinarily fine, possibly nanometer scale grains, or composed of materials with surface properties completely unlike typical silicate dust found in solar system comets. Hubble's polarization filters confirmed the Very Large Telescope findings. The polarization angle measures negative 18 degrees. Whatever material comprises 3I Atlas dust, it formed under conditions or from chemistry fundamentally different from local objects. Comment below. Does this sound like a natural comet to you, or something else entirely? October 2025 brings a new development that escalates scientific concern. 3I Atlas brightness begins fluctuating irregularly. Standard cometary behavior follows predictable patterns. As a comet approaches the sun, increasing solar radiation causes brightening. As it recedes, cooling causes gradual fading. The light curve should be smooth, following thermal models with minor variations from rotation or surface heterogeneity. 3I Atlas doesn't follow this pattern. Instead, it displays sudden, short-term outbursts, brief flares where brightness spikes dramatically, then returns to baseline. These events occur without warning, with no apparent connection to solar distance or heating cycles. NASA's latest update acknowledges the phenomenon. The language is careful, clinical, but the implications are clear. These outbursts suggest internal processes, pressure buildups beneath the surface, structural changes within the nucleus, possibly fracturing or collapse of internal voids, releasing trapped volatiles, or something else, something the models don't account for because we've never observed it before. Observatories in Chile and Spain have redirected instruments to monitor 3I Atlas continuously, hoping to catch these outbursts in real time. Each flare is being measured across multiple wavelengths, from ultraviolet through infrared, building a data set that might eventually reveal the trigger mechanism. But for now, the cause remains unknown. And with each irregular burst, the object's behavior diverges further from anything we've categorized as natural cometary activity. What could cause sudden pressure releases inside a comet? Several mechanisms have been proposed, each with supporting evidence and problematic contradictions. Theory 1, subsurface voids. Perhaps 3I Atlas has a porous internal structure with large cavities. As solar heating penetrates the surface, even minimal warmth could vaporize ice in these voids, building pressure until surface layers fracture and vent the trapped gas explosively. Theory 2, phase transitions. Certain ice structures can exist in metastable states, remaining stable until a small energy input triggers rapid transition to a different crystalline form. This transition releases stored energy, potentially driving sudden sublimation. Theory 3, electrostatic phenomena. The solar wind carries charged particles that bombard the comet's surface. If 3I Atlas has unusual electrical properties, charge accumulation could create sparking or discharge events that locally heat the surface, triggering outbursts. Theory 4. Exotic chemistry. If 3I Atlas contains compounds unknown in solar system objects, their behavior under solar radiation might follow completely different physics. We're attempting to understand alien chemistry using local rules. Each theory assumes 3I Atlas is a natural object following unusual but ultimately explainable physics. But there's a fifth possibility that scientists are reluctant to discuss publicly, yet cannot entirely dismiss. What if the internal dynamics aren't purely natural? Let me be clear. There is currently no evidence suggesting 3I Atlas is artificial. No radio signals, no geometric structures, no propulsion signatures. Every measurement is consistent with a natural object, just an extremely unusual one. But the combination of anomalies is forcing a question that sounds like science fiction, yet emerges directly from scientific data. Could there be internal structures or mechanisms we're misinterpreting as natural processes? 1I Oumuamua sparked similar debates. Its elongated shape, unusual tumbling, and slight non-gravitational acceleration led some scientists, including Harvard's Dr. Avi Loeb, to propose it might be artificial. The controversy divided the astronomical community. Most dismissed the hypothesis, but the questions it raised about how we identify artificial objects remain unresolved. 3I Atlas presents different anomalies, but equally challenging ones. Its activity violates thermal models. Its chemistry suggests formation in conditions unlike anywhere in our solar system. Its brightness fluctuations indicate internal processes we cannot explain. Its dust polarizes light in unprecedented ways. Individually, each anomaly might be explainable. Collectively, they create a profile unlike any comet we've studied. Dr. Avi Loeb, reflecting on 3I Atlas in an essay published October 29th, stated, "Each interstellar object rewrites our textbooks. 3I Atlas is telling us that there are chemical environments out there utterly unlike our own solar system. But is it only telling us about chemistry, or is the message more complex? An unexpected opportunity is approaching that might provide crucial data." NASA's Europa Clipper spacecraft, launched to study Jupiter's ice-covered moon, is currently traveling through the inner solar system on its trajectory toward the outer planets. Mission planners have confirmed that Europa Clipper will pass through regions of space containing charged particles and dust released by 3I Atlas. The spacecraft carries plasma sensors and particle detectors designed to study Jupiter's magnetosphere. But these instruments can also sample interstellar material. NASA's Heliophysics Division has coordinated with mission controllers to temporarily activate these sensors during the passage. If successful, this will mark the first time a spacecraft directly samples material from an interstellar object within our solar system. The data could be revolutionary: particle composition analysis, isotopic ratios, magnetic field measurements, information that telescopes cannot provide from millions of kilometers away. But there's another reason this encounter matters. If 3I Atlas is exhibiting any artificial characteristics, if there are structures or mechanisms beyond natural chemistry, close-range particle analysis might reveal signatures that optical spectroscopy misses. This isn't the primary mission goal. NASA frames it as opportunistic science, taking advantage of a rare alignment. But the timing is remarkable. An interstellar visitor displaying inexplicable behavior, a spacecraft positioned to sample its material directly, a chance to gather data that might resolve the mysteries multiplying with each observation. 3 confirmed interstellar objects have now passed through our solar system, each one completely different from the others, each one challenging assumptions in unique ways. 1I Oumuamua, September 2017, detected by Pan-STARRS in Hawaii, an elongated object tumbling through space, no visible coma, no cometary activity, yet slight acceleration beyond what gravity alone predicted. Debates erupted. Natural comet with invisible outgassing, rocky asteroid with unusual shape, or something manufactured? The questions remain unresolved. Oumuamua faded beyond detection before definitive answers emerged. 2I Borisov, August 2019. Detected by amateur astronomer Gennady Borisov in Crimea. This one behaved exactly as expected. Water ice sublimating predictably, coma and tail forming at appropriate distances. Chemistry matching solar system comets. It was almost disappointing in its normalcy, but that normalcy was itself reassuring. Interstellar comets could be conventional. 3I Atlas, late 2024. Detected by Atlas survey, and it fits neither pattern, active but wrong. Chemistry inverted, behavior contradicting thermal physics, brightness fluctuating irregularly, dust polarizing light impossibly. 3 visitors, 3 completely different profiles. What does this tell us? Either interstellar objects display extraordinary diversity far beyond what local solar system populations show, or we're encountering things that don't fit clean categories because categories themselves are incomplete. Every day that passes, 3I Atlas moves farther from the sunday. Every day it grows dimmer. By early November, its coma will fade below the detection threshold of most telescopes. The observation window is closing. Astronomical teams worldwide are racing against time. Spectroscopic measurements require sufficient light to analyze. Polarimetry needs clear signals above background noise. Imaging demands brightness above instrument sensitivity limits. Once 3I Atlas fades, the opportunity ends. No spacecraft can intercept it. Its hyperbolic trajectory carries it outward at 31 kilometers per second, fast enough to escape solar gravity entirely. Within months, it will cross beyond Jupiter's orbit. Within years, beyond Neptune. Eventually returning to interstellar space, drifting through the darkness for millions of years until perhaps encountering another star system. This is humanity's only chance to study it. The data being collected now will be analyzed for years, possibly decades. Every spectrum, every image, every brightness measurement. Researchers will extract every possible insight, building models, testing hypotheses, attempting to reconcile the observations with physics. But the raw data collection phase is ending. The telescopes will soon track fainter targets. The observation schedules will move on. And 3I Atlas will become archival data, frozen in databases, preserved in scientific papers, debated in conferences. Unless something happens first, unless one of these brightness outbursts intensifies, unless the Europa Clipper passage reveals something unexpected, unless new data forces even stranger questions, strip away speculation, focus only on confirmed measurements. What do we actually know? 3I Atlas is real. Its interstellar origin is confirmed through precise orbital mechanics. Its hyperbolic trajectory proves it came from beyond our solar system and will return there. It displays persistent activity at distances where standard thermal models predict dormancy. This is fact, not interpretation. The hydroxyl emissions are measured. The jet structure is imaged. The outgassing rates are calculated. Its chemical composition differs dramatically from typical solar system comets. Carbon dioxide dominates over water by an 8-to-1 ratio. This is unusual but not impossible. It indicates formation in a colder, carbon-rich environment. Its dust exhibits negative polarization. This has never been recorded in any interstellar object before. It implies particle properties fundamentally different from local comet dust. Its brightness fluctuates irregularly. Short-term outbursts occur without correlation to solar heating cycles. This suggests internal processes triggered by mechanisms not included in current models. These are facts, observations, measurements repeated by multiple independent instruments and confirmed by peer review. The question is interpretation. What physical processes explain these facts? Current cometary science cannot provide a complete answer. Every proposed mechanism faces contradictions. Every model fails to account for the full suite of observations. This leaves two possibilities. Either 3I Atlas represents an extreme case of natural phenomena we've simply never encountered before, or it represents something outside the boundaries of what we've defined as natural. The title of this video asks a question: could 3I Atlas be something far stranger than we think? That's not rhetoric, that's not sensationalism, that's the actual question emerging from the data itself. Scientists are trained to prefer natural explanations. Occam's razor demands choosing the simplest hypothesis that fits the observations. Extraordinary claims require extraordinary evidence. These principles have served science well for centuries. But what happens when the simplest natural explanations all fail? When the observations persistently refuse to fit established categories? When every new measurement deepens the mystery rather than resolving it? At some point, the question stops being, how do we explain this naturally, and becomes, are we sure we're asking the right questions? 3I Atlas is currently classified as a comet, an unusual comet, certainly, an anomalous comet with unexplained characteristics, but still fundamentally a natural chunk of ice and rock from another star system. But classification is not understanding. Labels describe. They don't explain. And when an object defies every prediction made about its category, perhaps the category itself is insufficient. NASA will continue observations as long as the object remains detectable. Research papers will be published. Data will be archived. The scientific process will continue methodically, carefully, rigorously. But behind closed doors, in conversations that don't make press releases, scientists are asking uncomfortable questions. Questions about whether our frameworks for understanding solar system objects apply to interstellar visitors. Questions about whether we'd recognize something artificial if it were designed to mimic natural processes. Questions about how we distinguish between extremely unusual and fundamentally different. These aren't conspiracy theories. These are the questions that emerge when data persistently refuses to conform to models. As I record this, 3I Atlas continues its journey outward, 31 kilometers per second, beyond Mars, heading toward Jupiter's realm, carrying its secrets with it. The brightness outbursts continue. The polarization remains negative. The jet persists at temperatures where it shouldn't exist. And scientists worldwide watch, measure, calculate, trying to solve a puzzle that grows more complex with each observation. Could it be something far stranger than we think? The honest answer is, we don't know. And that uncertainty, that gap between observation and explanation, is precisely why this object demands attention. Not because it's definitely artificial, there's no evidence supporting that conclusion, but because it's definitely anomalous. And anomalies in science are how we discover that our understanding has limits. 3I Atlas is either teaching us that interstellar objects can exhibit natural behavior far beyond our current models, or it's teaching us that we need to expand what we consider when evaluating objects from beyond our solar system. Either way, it's a lesson we need to learn. Because 3I Atlas is the third interstellar visitor we've detected. The Vera Rubin Observatory, coming online soon, will spot dozens more, perhaps hundreds. And if even a fraction of them display characteristics this puzzling, we'll need better frameworks for understanding what we're seeing. The universe is vast. Our experience is limited to one star system. Every visitor from beyond expands that experience, challenges our assumptions, tests our theories. 3I Atlas is doing exactly that, testing us, forcing us to confront the possibility that our categories, our models, our definitions might be too narrow to encompass everything that exists beyond our planetary neighborhood. Comment below, what do you think 3I Atlas really is? And subscribe, because this story isn't over. The data is still coming in. The Europa Clipper passage approaches. And somewhere beyond Mars, an object from another star system continues doing things that objects aren't supposed to do. The warning isn't about danger, it's about humility, about recognizing that the universe contains phenomena we haven't categorized yet, about staying open to possibilities that make us uncomfortable. Because 3i Atlas is telling us something, we just haven't fully understood the message yet.